All right, so in the last video, we were working on this problem. I asked, is 213 in the span of these two vectors? Which, remember, this is the same question as, can we write 213 as a linear combination of these two? So we have to figure out, can we find x1 and x2 such that 213 equals x1 times the first vector plus x2 times the second vector, right? And of course, this is a vector equation. All right, so the way that we could do this to solve for x1 and x2 is to set up an augmented matrix and actually solve for those. Okay, so the first thing we want to check out is what happens after we row reduce this. So if you need to pause to verify that you were able to row reduce this correctly, definitely do that. So note that we got so we got x1 is 1/2, x2 is 1/2, but then down here we have a weird inconsistency. We know that we don't have a solution here. 0 plus something plus 0 will times something will never equal 1/2, right? So this is actually inconsistent. So it doesn't matter if we were able to solve for x1 and x2 here, because we have this row of zeros equaling another number. This system is inconsistent, and therefore we cannot write this vector 213 as a linear combination of these two. So the answer would be no, this is not in the span. Okay, let's look at another example. All right, so we want to determine if the vector b, which is in R3, 2, -1, 6, is a linear combination of A1, which is 1, -2, 0, A2, which is 0, 1, 2, and A3, which is 2, -1, 6. Okay, so we have to determine, is B a linear combination of these three vectors? Well, what we're really asked to do is to find x1, x2, and x3 such that x1 times A plus x2, sorry, A1, x2 times A2 plus x3 times A3 equals our B. All right, so you should be able to look at this and find a fairly obvious answer here for x1 and x2 and x3. All right, so I don't really like to use the word obvious, but here would be an obvious answer. We could let x1 equal 0, x2 equals 0, and x3 equals 1. Plug those in, that should work out. All right, what if we wanted to find all answers? You guessed it, augmented matrix. Okay, so I'm going to set up an augmented matrix with these three vectors. And set it equal to our B here. And instead of actually going through the row reduction, I'm going to say, oh, we did it. and we put it into RREF. You can always verify this later, but just to save time. Okay, so let's say we set up our augmented matrix as we did. We were able to row reduce it into RREF. We got zeros on the bottom, but great, it equals 0. That's great, we're consistent. So we should be able to find a general solution. So in our general solution, we can figure out what x1 is, x2 is, and what x3 is. So x1 is going to be 2 minus 2x3. X2 is 3 minus 3x3. We're seeing we're going to have a free variable. So x3 is free. All right, so that is our general solution. We could also talk about a particular solution, which is actually what we have up here. So a general solution tells us all possible solutions. It's the solution in general. Particular one tells us an exact solution. Which one? Let's choose one of these many solutions. So we could choose this one up here, or you can choose anything you want x3 to be. So you can choose whatever you want for x3. I am going to try to make things easy for us, and I'm going to choose x3 equals 0. You could choose 5, you can choose 1,000, whatever you want for x3. And then so to find the x1 that goes with it, I will just plug in 0 here. So x1 is 2. And x2 is 3. So a particular solution would be 2, 3, 0. Okay. And so we can use this to write our b, 2, 1, 6, as a linear combination of these other vectors. All right, so we can write our linear combination. And remember, we got a free variable, so there are infinitely many of them. So I'm saying this is just one of the linear combinations. So I'm going to go with 2 times my first vector plus 3 times the second vector plus 0 times the third vector All right, so we were able to write it as a linear combination, and because we were able to do that, 2, -1, 6 is in the span of these three vectors. So let's write that down. We can say that 2, -1, 6 is an element of the span of these three vectors. But don't forget to notice we had a 0 here in front. So we actually don't even need this third vector to come up with 2, -1, 6. So we can also say that 2, -1, 6, our b, is in the span of just the first two vectors. because we can write it as a linear combination of only the first two. Also, our b is the same as one of these. So we can write our b and it's in the span of itself. All right, and so that would be the end of the section on spans. And one more thing that I want to point out, if we haven't mentioned already, when we set up something like this with scalars in front of vectors and set it equal to something, this is called a vector equation.